yes, this is going to be part two of um, Automatic Kernel Fusion, or rather specifically Burn's implementation of Automatic Kernel Fusion. And I think in the last, in part one, that is, we sort of went through the 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 basics, I'd say, of what Automatic Kernel Fusion is, um, and uh, pretty much why we need some level of abstraction, because you have GPU kernels. Those are programs that are going to be launched, uh, or rather, in order to run any code on the GPU, you'll need the CPU to sort of launch kernels onto it, and then the GPU is going to do the work and provide a result back to you. Um, so in that entire process, we talked about the way, for example, machine learning models and frameworks that allow you to build machine learning models like Burn work, is they use this concept of building out what's called a compute graph, right? And then there's quite a bit of complexity involved in how you should construct the compute graph, how you should be able to, look at the graph and say, okay, I have opportunities over here to optimize the graph. And that's sort of what this little picture over here, it's not an accurate representation, but just, for intuition. It's, let's say there is a scenario where you have um, a tensor, some tensor, no, God knows. You just want to basically do three different operations on it. You want to be able to do some scalar multiplication, some scalar addition, and then apply a tanh. Forget about what the operations are, but this is the sequence of operations that you would like to apply to this one tensor. The output of this operation goes into the input, goes in as input, and then likewise, that chain of operations will produce Z. The thing with machine learning frameworks, especially with things like PyTorch and all of that stuff you've already seen, is there is this thing called kernel fusion. Because what usually happens is if you were to naively go ahead and sort of use a GPU to do this work, or you can go, you probably have a tensor that's, I don't know, a million elements or 10 million. I don't know if you have a 10 million element strong tensor, but anyway, let's say you've got a large enough tensor, and I'm just talking about 2D arrays as such. And you were to apply a scalar multiplication and an addition and a tanh all in sequence, then there would be, it'd be very, very slow because you need to take this tensor, put it in the GPU memory, which is global memory, and then from there launch the GPU program, which is going to use that tensor as input and then compute and then push the result back into global memory. So this data movement uh, between global memory to GPU shared memory to the registers, etc., that's a huge hit. So the overarching theme that you're going to hear in these computing frameworks, or rather in machine learning frameworks, is that it's not compute that's the problem. It's data movement, right? Both when you're writing the model itself and when you also want to do something like training and distribute that training workload across multiple GPUs, which is called multi-GPU programming. And that's where you'll find things like NPI, NVIDIA's Nickel, and I think there's NV shared memory, a bunch of different libraries. Again, they're trying to make it easy for you to sort of do multi-GPU programming. But effectively speaking, data movement is the bottleneck, to say, right? That's pretty much where you would see a lot of optimization. That if you see any optimization in any framework, you can bet that it has to deal with, I mean, the optimization is to deal with the data movement problem, because data in GPU global memory. So there's this memory hierarchy that we have in GPUs. I think I've talked about it quite a bit. But just to recap it, You've got global memory, you've got shared memory, which is programmable. It's like an L2 cache. And then you've got things like register memory and local memory, etc. So obviously local memory, register memory is going to be the fastest. It's like kind of a couple of nanoseconds and stuff like that. And then as you keep going down, as you keep going further and further away from the cores, your number of cycles to sort of move data in and out is going to jump. And when you start adding all that up, you know, it's not going to be really what you'd say fast. So all in all, this is why you'd want to take, instead of having to launch 3 different kernels to do 3 different operations, uh, on maybe one element or one piece of data that's going to be used as input in a chain, in a sequence, that is, you could probably just turn that into something like this, right? You could say tanh, tensor1, this is like you're writing this code in, like this, but I mean, obviously, this is not exactly why, if you write it this way, it's not going to automatically go ahead and run in such a fashion. It is going to do a couple of things for you. But in any case, here, what we're basically talking about is this particular compute needs to be sort of, you need to sort of have a scenario where you're saying that, look, these 2 intermediate values that are produced, one is right after tensor 1 undergoes a scalar multiplication and produces some intermediate value, and then undergoes a scalar addition and produces some intermediate value. You don't need those 2 values to go back to global memory, right? You just don't need them. You only need to write the last piece in this example, and the one that we discussed. And that's the whole goal. How do you ensure that that happens? And I'll just talk about, what we discussed last time. We talked about Burn's genetic tensor abstraction. We've sort of seen it. And I think I sort of went through an example with you guys as well, where uh, you can see, the tensor is basically, if you were to go ahead and look at its definition, it's generic over B, D, and K. So this, I don't want to like rehash everything because we've already been through it. You can watch part 1 if this is something that you'd like to know. So it's generic over a backend, and I talked about backends being things like, where is that? Rather than me talk about it, let me just see. Uh, by the way, my notes are over here in case anybody wants them. So I've already linked them in the description as well of the video. So you'll find them there as well. In part 1 and part 2, it's the same notes. So you'll find them over here. What was I looking for? I was looking for, I think I forgot what I was looking for. Yeah, the backends. So I think backends are supposed to be here. Yeah. Okay, so, and we also talked about CubeCL, what CubeCL is, and how the Burn folks are actually building out a really, really, nice project where, with all this power and Rust, uh, it's a shame that you can't, directly get to use that in GPU work before. But now with Burn, I think you're almost there. Uh, so effectively, you don't write GPU code or what you call shader code, kernel code, whatever that is, in a language like Rust. If you can write it in things like C++, why not in Rust? Was the question. And I think that's kind of where we've arrived at. CubeCL is a really nice project where you can take Rust code and convert that to pretty much target any GPU native instruction set. And there's ways to do that. I've discussed that a lot in many, many, many videos. But here's what we mean by that. So let's say I've got a web GPU backend. Now, this is a standard that pretty much every browser window supports. So that's why it's called web GPU. But web GPU also has implementations outside the browser. And that's called If for Rust, that's WGPU. This is what's powering a lot of the graphic stuff in the Rust world as well. So basically, you would write your code if you're using the WebGPU framework, you write your shader code that gets to run on the GPU, that gets compiled down to the GPU native instruction set in what is called WGSL, WebGPU's shading language. So basically, with CubeCL, you can just target this, that you can write your shader code in Rust, and it will be translated into WGSL code. When again, WGSL code will be translated into the native shader format. So there's a nice pipeline over there, and I talked about it quite a bit. In case you're interested, I'll link one of those videos as well that goes through this. There's all these backends that are currently supported. All right, that's pretty much most of it. You got NVIDIA, AMD, Apple, and then for the rest, you could just do MGPU. So that's about it. As you might be wondering, for the Android world, when you think about things like Qualcomm and all those folks, where are they? You pretty much just target web GPU, and I guess you're there. Yeah, I've not really seen Qualcomm in this space, the open source world or whatever. I, I just haven't seen them. That's the only other big player, I think, considering their presence in the Android space. But anyway, so that's the backend. So you're generic over that. You're saying you can go ahead and create tensors, and then you can work with, let's say you have a GPU of this kind, or that kind, or whatever, it'll work. And then D is dimensionality, and K is the element type, which is defaulted to float over here. So yeah, so that's the Burns tensor abstraction. And then we talked about composability of those backends. So you can have a backend, and you can basically go ahead and do all of your ML work, great. But if you want to say, I want the ability to be able to, have automatic kernel fusion, then you could just compose that. You can have, say, this tensor abstraction. You don't need to worry about whether you're using the right tensor abstraction, because it will just say, okay, does your backend support, can we just use your backend along with fusion support? We can. So that's something that we talked about. And then there's client server abstractions to make that all seamless, etc. Great. We also looked at, let me just minimize this. We also looked at how a tensor is created. And the simplest method is this from data thing, where you call this and you're going to get a tensor. Now, because you've already specified things like web GPU and the backend, is all that stuff is specified, this particular tensor that you've allocated will be sitting in GPU memory, right? That's, that's a lot packed into that single line, and I've covered that in the previous, in part one. So we can look at that. Now, without spending too much time just recapping everything, and then we also talked about the three different operations. Like for example, for these three different operations, if I was to look at exactly what GPU code is generated, I sort of walked you through that and said, okay, there are three distinct kernels, the first, second, and third. The first one does some setup. The second one is, again, doing more setup. And then the third one is where you would pretty much see, sorry, the fused kernel is where you'd actually see your code being, you know, uh, your code being pushed to the GPU and leveraging the GPU to do your work. That's kind of what I mentioned here. So you see that all this abstraction exists because you don't want developers who really don't need to be working with the nitty-gritty details of the GPU programming models, etc., to figure out how to get their work done. You're writing a machine learning model, and you want to focus on the fact that, okay, I have tensors, I'm going to be running these operations on them. I want it to be as efficient, as performant, as fast as possible. All right. For that, I don't need to learn the GPU programming model, which is called SIMD, SIMD in NVIDIA's world, or SPMD, or whatever it is. And then you talk about the makeup of the GPUs, all that stuff is a lot. You're not going to get too far. You're going to get specialized experts to only do that. And PyTorch wouldn't be what it is today if it went down that road. So frameworks sort of provide that abstraction. Burn is that abstraction in Rust. And why is it different? The way I think about it is because it's leveraging all the goodness of Rust. You know, uh, with something like Python, the problem is you've got that three language problem, which I believe Mojo is trying to solve. I do have questions about that though, because Mojo is actually, it's a wrapper around MLIR, which is actually written in C++. So I know that they're going to do a great job and they're trying very hard and stuff. But at the end of the day, if something goes like, if I really want to figure out what's going on and whatever's offered in the Mojo framework or Mojo, API is not enough. That means I only have Python knowledge. I only have Mojo knowledge. I don't have C++. So I'm still in that, language boundary problem. With this, it's all Rust all the way through, including the shader code. So that's really nice. So don't get me wrong, Mojo is great. You can write shader code directly in Mojo. I've seen that. And they've also open sourced their kernel library and a lot of other things, etc., which is all good. But yeah, question. Still, we'll see how that works out. Then the other things are about, the ability to actually go ahead and leverage all that. Right, by now, I think Rust is a mature language. It's got the things that you need to deal with a whole bunch of problems. Um, and you would see that in this. So for example, I did see that when I was trying to read some Mojo code, I was trying to go through, okay, how do we do X? And I didn't really get very far because I really needed to move into MLIR space and learn that part. That means I need to go figure out C++ and all the stuff that comes along with it, especially in the design that went into MLIR. Here, that's not the case. I pretty much was able to understand the code base from the get-go. And that's a huge win, I would say. Apart from all the other pieces, the way you're building out these abstractions, the way you can reason about them, the way you can build abstractions that are not just performant, but also relatively easy when compared with the alternatives to get going with. I mean, if you know nothing and you tried something, you tried, yeah, and you know a little bit of Rust, maybe this is much easier. At least that's my opinion. So anyway, so that's why Burn. Now, with all that said and done, I just want to quickly focus on the meat of the talk, which is how does Fusion actually work in Burn? Let's get into that. And as usual, we'll be using these three instructions or these three operations, that's the word, without delving into the complicated examples, because that's all we need to know what the architecture looks like, at least in Burn. So keep these in mind, but before we jump into it, let's just look at some little pieces. I think we sort of touched upon it in the last part, but let's just go through this again. So before we talk about Fusion and how it works exactly, just some intuition as to what do you need to be able to fuse operations or kernels, as they call them. So let's look at that first. And so understanding reads and writes. So one of the first things that you will need to do is, in the context of Fusion, you will need to know, like, for example, the tensor that we were talking about. I don't know why I minimized that. So this particular tensor 1, you would like to know which operation reads this data. Tensor is tensor data. It's an array. some sort. There is no multi-dimensional arrays, etc. in computer memory. It's all a sequence of bytes. Okay, so just know this much, that reads and writes. So which operation is attempting to read a particular piece of data, in this case our tensor, or which operation is attempting to write to some piece of memory that we have. Because as I said, if you remember, uh, data movement is the biggest problem. And data lives somewhere, it lives in memory, and you need to move it from one memory to another memory, maybe. And that's kind of what you want to focus on, right? The interaction and the access patterns and the dependencies, what we call data flow dependency, is what we need to actually track when we talk about fusion. All right. And the way that sort of happens in Burn is there's a lot of abstraction. So let me put it right out there. I'm just showing you the last piece, which is fuse block builder. You do a bunch of things, and then you'll get this thing called a fuse block. All right. That means a block of operations that has been fused. All right. So just keep that in mind. So that's we'll get to that part, but just know that at the end it will look something like this. And if you notice about this, if you notice something about this data structure, you will see reads and writes and tensor writes. Exactly what memory access patterns, and you should be able to sort of intuitively tell this has something to do with memory, right? So let's look at that. So the reads field over here is a map. It's trying to tell you, okay, this is the ID of a particular tensor, and also what sort of precision that we have and what sort of layout that we have. So basically, which tensors have been read for which operations. So is this tensor going to be read by this operation? That's kind of what we're trying to get at over here. So when an operation needs to read a tensor, it's registered in this map. This helps the optimizer which tensors need to be loaded from, to understand which tensors need to be loaded from memory. That's sort of why we need to track this information, and we're tracking it in this data structure over here in Burn. Likewise, you got writes. I'll come to this particular part. It's yeah. So when an operation produces a result, it needs to be stored somewhere. And if it's going to be stored somewhere, is that global memory, shared memory, the hierarchies of memories that we talked about? That's kind of what this aids with. And then there's tensor writes. This thing actually does a little more. I'm just going to say that, if you're going to be writing tensors to global memory, this thing is specifically tracking that, at least as far as my understanding goes. Now, here's the other point. This is all my reading of the code. Now, if I did get something not so right off, I'm assuming it's right because I just validated stuff. But if I did get something wrong, please feel free to correct me, because yeah, I'm not the author here. So yeah. All right. So that's effectively what I wanted to talk about. So the intuition is, if you want to build, if you want to build a fusion, if you want to build fusion capabilities into a machine learning framework, what do you need to do? You need to go ahead and look at things like this. You need to figure out, okay, what's the memory access patterns for the data that you're dealing with, right? How do you track them? How do you build, uh, data structures that can actually track that for you and basically allow you to build a fused operation or a fused kernel. All right, so that's that. Now, yeah, this is sort of what I'm talking about. Why tracking reads and writes is important. Just to sort of talk about the notes that I made is, you want to minimize global memory accesses. You want to keep intermediate results in faster memory that is registered in shared memory. And if there's an opportunity to coalesce some memory operations, that means you don't need to really do multiple copies. Maybe you can just do a single copy, right? Or maybe you can combine a bunch of different copies into just one copy. You don't know. You could probably do all those things over here. And you can also do things like data dependency analysis. Like just by being able to track which tensor is reading which piece of data, you can say, okay, which operations depend on each other, which operations are can possibly be executed in parallel, which operations can be fused together. So if you know the first two, you can probably come up with an idea of saying, okay, these can be fused together because they don't depend on each other. Sorry, uh, they do, things in a sequential manner, one after the other, maybe so you can just club them together, right? And then memory allocation, how much memory is needed for intermediate results. So then you can write the right kind of kernels saying, okay, I only need this much memory, I don't need more than that, etc. So that's effective utilization of your GPU memory. Um, when memory can be reused, when memory needs to be allocated, all these pieces are what you'd be able to tell if you track, you know, reads and writes. Simple. That's kind of what we're going for. And here's the other example. I think we sort of went through this already, but just to sort of highlight this because I'm going to go over a high-level picture of the Fusion architecture in Bern. Uh, Obviously, going through the entire code base is going to be mental because we're going to be there's just going to be a huge number of abstractions as I'll show you anyway because I made a note just for my reference. Yeah, so we'll just look at the high level picture, sorry. But before that, just the intuition. The intuition is this, where for our simple example, we've got three operations, and we start off by saying, okay, tensor one, this is the raw tensor that I just created. I placed it in GPU memory. Great. It's sitting in global memory at this point. Then there's a constant, which is, so let's just take the first part, which is this. Okay. In there, we're seeing the scalar is also something that needs to be read. Now, ideally, this thing doesn't need to be sitting in global memory because it's just, an integer, and we could probably just pull it in, or you can just probably pull it into register memory. That's possible. So you read it in. But anyway, for now, you need these two reads. And then the operation from this is going to be this is going to be a result. That result is going to be sitting in, say, temporary one. It's a temporary register. Likewise, the scalar addition also does the same thing, but it takes the input from the previous operation and a scalar called 1, which is the addition of 1, and writes that to another temporary variable. Let's just call it y. And the last operation is tanh. This one reads y, again, an intermediate result, and then finally applies tanh on it and then writes that out to global memory. So effectively speaking, these two temps, the temp and the temp1 and the y, you don't need to go back to global memory for that. That means you don't need to write it and read it back, right? So the optimizer, the whole idea of Bern's fusion optimization frame, capability is going to be, or any, for that matter, any machine learning framework is going to be, okay, hey, these temp1 and y are intermediate results. They don't need to be written to global memory. Instead, we can just keep them in registers or shared memory, whatever works for us, depending on how complex the figure offer that we have. And we can ensure that only Z needs to go out to global memory. Once we have this picture, then we write our kernels, right? And that way, we've just fused that entire kernel and said that this is actually one kernel, not three different individual kernels. Again, to just repeat things, kernels are just programs that run on the GPU. All right, and this is kind of what happens in the fuse block builder. Right now, I won't directly jump into this abstraction called the fuse op, etc. But effectively, you're tracking all tensor reads, both from global memory and intermediate results, and then you're saying, okay, this tensor ID is associated with all these tensor operations. So which operations read from that tensor? Same thing goes for writes, and then that's why I was saying tensor writes is a little different. This one determines the intermediate results that need to be written to global memory. That's the job. And then filters out those intermediate results that are not going to be written to global memory and only the ones that are going to be written to global memory. All right. So yeah, I do have another yeah, I did quite a bit of homework to say how can I nicely explain this, and this partly if I ever come back, let's say after a couple of months, I should be able to pick it up very quickly. That's why I have, you know, a lot of elaboration over here. Anyway, so the example over here is um, this particular operation reads tensor1, and then you're basically saying, go ahead and generate this operation that will take an input. You'll have a local zero over here. You start with a tensor, then you assign this. Yeah, you read tensor ID in, and then you get two into a local variable, etc. And then you go ahead and compute your uh, temp1, which is again a local variable. Same thing goes over here. You get temp1, you take your tensor temp1, and then you go ahead and add 1 to it, and then you have your locals 2. Again, in the last operation, you will be able to see that the final result, once produced, you can go ahead and so this stuff, this is not to be visualized from the idea of the actual GPU itself, but this is just to say that okay, this is how the optimizer is sort of looking at things. When you do what is called the optimizer build method, there is a bunch of levels of abstraction over there. But when you do say, okay, build me this optimization, this is exactly what's going to happen. You're going to see that temp1 is only read by the add operation, so it's not written to global memory. Y is only read by tanh, so it's not written to global memory. Z is the final result, and that's what you want to be able to see when you do print out the value of the tensor. So this needs to be written to global memory. It's kind of what happens. And effectively speaking, that's the intuition for what you should be thinking about when you think about how do you add the ability to fuse kernels into any framework. You need to be thinking about these things. That's the only thing I would say. The rest of it is just implementation specifics. But so let me just sort of uh, pause over there so that I don't overdo the whole explanation part. I hope that is good and they give some sort of intuition because that's important. And then let's get to the actual part, which is how does Burn actually do this, right? So I've put together what is my understanding of what Burn does. So again, please don't hold me to this. This is after me reading the code base and actually also asking the authors as well, is this right? And I think they said pretty much close enough. So this is close enough. This is not exactly the right, the authoritative source to say that this is a close enough approximation of what happens in the fusion part. Okay, so the high-level fusion architecture in Burn is quite simple. If you think about it, the first thing is those 3 operations. We need to know what the operations are and the resources that they will need. In other words, the data that they operate on. We'll need all that information, right? So the first thing to do is actually collect that information into what's called an operation queue. And this is sort of referred to as a stream. So I'll give you the high-level view, and then we'll sort of dive into a few more details. And I'll leave my notes on the stream so that, if there's pieces that are not adding up, you can probably look at them. But yeah, I'm not going to be the nitty-gritty implementation detail because that's just, trust me when I say this. There's a ton of abstraction in here, and it's just going to be me sitting there talking about, okay, which function calls what and why this happens, etc. So the first thing that you see, as you see over here, let me just pull this up so that I can have I can do this. I can just show you this and this. Yeah, that should suffice. Okay, so we have the operation queue. So all three operations, the scalar multiplication, the addition, and the tanh sort of go into this queue. And then there's this data structure called the stream optimizer. All right. The stream optimizer is basically going to create blocks of these operations that you've collected. You've just pushed all your instructions into an operation group. You called it the stream. You called it a stream. And that's very much in line with what other uh, programming frameworks use. Like, for example, NVIDIA's CUDA has things like CUDA streams, and um, then there is Vulkan, and all of them, they have similar abstractions. I forget the name for it. It was called something. Anyway, there's very similar abstractions across the board. Effectively speaking, a stream is a sequence of operations, usually ordered. That means the way you've written them out in your code. That's a sequence in which we expect to be running that code. Not necessarily, because if the optimizer sees a way to say, okay, we do not change the meaning of this code that you've written, but we can reorder something, that's also fine, right? Yeah. If it's faster to execute something in a different way than it's been written, then you probably want to do that. That's the idea anyway. Um, so yeah, you put all these three operations in the queue. Then there's this data structure called the stream optimizer. It's basically going to take, you're basically going to try and insert each operation into a block. So it's sort of holding these, yeah, let's just say that, it's sort of creating these blocks, saying, okay, which blocks contain operations that are probably fusible, right? That's it's kind of how I would put it. That's my, let's say, reading of it. And then let me more to the side. Yeah. Yeah. So then what happens after that is, in our simple example, you're going to say, okay, there's the first one, which is I'm going to create the tensor. So that's first operation. And then the second operation, the second thing is the second block's probably going to contain these three operations, because I think they're all fusible. Obviously, they are fusible. So uh, that's the intuition that you're trying to build. So for each new operation, the way you're going to try and insert each instruction is you're going to actually ask the block, are you going to accept this operation or not? And it's going to do a couple of things to say, okay, so I've accepted the first operation. Now, any time you create a block and you want it to accept the first operation, it'll accept it. The second one is going to check whether this operation that you're asking me to accept is sort of dealing with the same data or not, right? So you got to track it along those lines, data dependencies. And then once that is done, then you move to this other data structure called the blocks optimizer. So you go from operation queue, stream optimizer to blocks optimizer. In the blocks optimizer, again, uh, it'll do a simple thing called merge block merge pass. That means can multiple blocks actually be merged? You don't need to like have a single block. Only if using a single block, maybe you can fuse multiple blocks. We'll probably do that. So it'll try to do all those things, but then it'll go ahead and say, okay, the blocks optimizer will actually defer to the block itself to say, okay, if I've constructed a block, you also have what you call optimization builders attached to each block. That's the one that actually does the optimization, right? So that's sort of what I wanted to, I'll come to the flow of things just so that you know. So just know that you've got an operation queue into which you probably insert all your operations. And for all intents and purposes, the operation queue is your compute graph. That's the sequence of ordered operations that you want, to have executed. either on the GPU, CPU, wherever it is, but that's what you want. You want these operations in this order to be executed. And the first thing you start to do is collect those operations, then sort of group them together to figure out which ones can be grouped together based on the probability that they are fusible. And then you further start looking inside each block and saying, okay, let me see, can I do further optimizations like merging blocks, etc. But once I'm ready, I will then say, okay, now I think that this particular block, the operations inside of it can be fused. I will go ahead and ask. I will go ahead and ask the block itself to do the optimization part using what's called an optimization builder. Once the optimization builder has done the job of actually saying, okay, here's a fusion plan, that fusion plan is going to go and get stored somewhere, right? That's the execution strategy that you see here. So yeah, so that's the high level view. That's the way I would put it. That's the high level view. And you could probably see that here as well, where I'm saying, so when we do, sorry, just have to do this because this is a bit of a headache. My OBS kept crashing, so I'm just using whatever works. Right, so once we know that there is a fusion plan, we'll go ahead and take those fusion plans and put them somewhere. And that's what you called an execution plan store. And that's going to become part of our execution strategy, right? So that's the highest level view that I can sort of talk about. And this is sort of how the Burns fusion architecture sort of works. So just keep this in mind as I go through a little more detail before I just break. And I think the third part is possibly or if I can make it, I'll combine that in this stream itself. But once the optimization is done, how do you actually generate the actual cube, the kernels? So first you generate the CubeCL kernels, and then you generate the actual, kernels for the right GPU target. Okay, let me just close this. So that's the intuition or rather the very high level picture of how Burns fusion architecture, what it looks like, at least my view. And then here's what I was talking about, the operation queue. This is the data structure. Like, I'm not going to go to every little detail, but it should give you an idea. And then Burns' lazy execution system. I talked about this in part one as well, where I said the final result. So whenever you want to print this tensor, that's when the whole fusion and the entire pipeline kicks into work, and then the job gets done. So that's why it's lazy. Okay. There's some plumbing that's been put together to sort of make that work. That's not important, but yes, that's how it works. And then here's where everything kicks off. So you remember I talked about a stream, and then I talked about an operation queue. The operation queue is actually part of a data structure called a stream, and a stream is part of a data structure called the multi-stream. Multi-stream is basically a collection of streams. A stream is a single collection or a single sequence of operations. So basically, this is where everything kicks off. This method will drain a stream, and the entire stream is going to be processed. It's going to be processing. So let me just give you a minute, just a minute.